Good day. Well, we introduced in the last lesson or two that the main problem that we're going to solve with calculus this semester is this problem of area. How do I measure the area under the graph of a function when the graph may not be in the shape of a line, like it might be a curve? I've divided this, I've drawn a function in all three pictures, and I've shaded the area under it in gray, but I've approximated the area three different ways, all with rectangles. In fact, all with 4 rectangles or 5 rectangles. And so the image on the left shows what I would call left-sided rectangles, because as I divided this interval into equal parts, we always measured the height on the left side of that interval. And so that's the upper left corner that touches the graph. In the second image, the blue rectangles, I call these right rectangles because it's the right edge that determines the height of the rectangle. So on the first interval, the rightmost point, I graph the height of it, and that's the height of the rectangle. I do that the same way throughout. In the third instance, it's the same function, same number of intervals and everything, but what I did this time was halfway through each interval, I marked a point, and the height of the function at that spot is determining the height of the rectangle. And so each time I go halfway across, that's where I measure the height of the rectangle. All right, so 3 different approaches. I can see that it's probably the midpoint method that's giving me the most accurate results, because in this case, some of the rectangle lies over the curve, but there's a number of it that's underneath, and so maybe the net result is a pretty good estimate of the area under the graph. But all 3 are estimation methods, and all 3 have the same basic idea, that the area of each rectangle, which approximates the total area, is found by taking the width of each rectangle, which we denote the change of x, and that would be like the distance across each of these strips. Each rectangle has a height measured by some value of the function. In the red rectangles, it was the height at the leftmost point. In the blue, it was the height at the rightmost point, and in the last one, it was the height at the midpoint. Either way, we're picking a point within each subinterval, we're measuring the height of the function, and that becomes the height of the rectangle. And now, summing them all together, or adding the areas all together, gives me an approximate area. And the n is the number of rectangles. The change in x is each of the rectangle widths. And then the function value gives you the rectangle heights. So as long as you recognize that really we are adding together rectangle areas where we have the height multiplied by the width, that's really all there is to get here. Now the way we could improve this, see obviously when I only have 5 rectangles, there's lots of error in these left and right sums, would be to improve this by just increasing the number of rectangles. And so if I want to get the exact answer, the exact area, this is where we improve and improve and improve by adding rectangles together again. So I'll keep the same notation, but this time we will increase the number of rectangles by just letting n approach infinity. That would tend to make all the rectangles extremely skinny and thin, but having more of them would fill in the space and give you the exact answer. And so notice the type of summation is the same, and so we have a special name for both of these sums, and it's just named after someone. So this is a Riemann sum. I kind of just refer to them as rectangle sums because we're just summing rectangles is the basis for how this is formed. But they are properly called Riemann sums. And you're going to hear me refer to Riemann sums a number of times today. Well, I'd like to look at that special Riemann sum notation in the next slide here. So I'm using the expression for a Riemann sum, and for this purpose, we recognize that this Riemann sum is also a rectangular sum, and which gives us the area between the graph of a function and the x-axis. And so I've also applied the limit here, which means it's the exact area, not an approximation. And we're going to take this over these different intervals. So I would encourage you to pause the video here after I talk about A and maybe see if you can answer the other three. So in the first one, it says, what is the value of this Riemann sum, the limit of it, in other words, the exact area on the interval 0, 3? Well, I would just simply take my highlighter, highlight the region that's contained on the interval 0, 3. Notice that this is a square, 3 by 3. And so even though I could draw a series of rectangles in here and add them all together, I don't have to because this whole region is just a square, 3 units by 3 units. And so this area is 9. I encourage you to pause the video and try this idea on the other 3 intervals before I talk about them also. Well, let's finish off the other 3 intervals. So I'm going to highlight as we go, and notice that in the next region, I have to go all the way from 0 to 5, which means I'll take what I already had and add on this extra bit here. And if I just look at my graph paper, I notice I'm adding 3 additional full squares and then 2 half squares. So I'm adding 4 square units onto the previous answer, which makes this value be 13. To go from 0 to 8, I'm adding 2 additional whole squares and then this half of one. So I should be getting 15 and a half. Now I hope you think carefully on the last one. Maybe you're wondering what we should do here, because I definitely see that if I just ended this at 10 and I go all the way across, I definitely am getting more area here. Maybe you're wondering what I do with that, because does it matter that the graph is below the x-axis? So the area of this little region here, this triangle, is 2. All right. In fact, I'll label the other ones. The original one was 9. Adding this extra space on the next one was 4. And then this extra one here was 2.5. What do I make with this 2 here? Is it really 2? And is the grand total here 17.5? Or is it something different? Well, the area there is 2. But let me go back to the definition of what we're trying to do. We've defined this to be a sum, or a Riemann sum. And if you were drawing little tiny rectangles in there and we're moving from left to right, well, the delta x, the width, is a positive number as we go left to right. However, the function values that define these lengths here are negative. So as I found the product of the function value times the width, I'm actually going to get a negative number because the function value is negative, but the width is positive. Which means adding all that together is adding up a bunch of negative numbers, which means really I'm going to get an answer -2 here. And so the correct way to see this is that the grand total should actually be 15.5 minus 2 and get 13.5. So remember that as we talk about this for the next little while. This Riemann sum gives you the area if the graph is above the x-axis. It's really what I would call the net area if we're talking about some parts being above and some being below. Parts below need to be counted as negative numbers, and so we have to subtract areas in a case like this. Now, if I go back to the last slide here, we need to mention now that this Riemann sum, being like it is, could have positive values, could have negative values. It really means the net area, not just the total area. I'm going to introduce a new symbol here for us. And so the exact area, or the net area, I'm going to now add this limit of this Riemann sum. I'm now going to define a new symbol for you. I'm going to borrow a little bit from the Riemann sum, the function and the dx instead of delta x. But this symbol here we call a definite integral symbol. And it provides a shorter way, or more abbreviated way, to express all that we're doing with this Riemann sum. In fact, it tells us a little bit more information, because notice in this Riemann sum, it doesn't specify what interval we're using. That would have to be described ahead of time. But in this integral symbol, the a and the b are specified, and you know exactly where to start and where to stop. So if I were to go back to the previous slide and restate these problems, I could describe this problem as being the definite integral of f of x on the interval 0, 3. And interpreting that as the area of the graph, that has a value of 9. This one I could interpret as the definite integral of 0 to 5. And that's 13. I could express this one as the integral 0 to 5 of f of x. And the last one now, the net area, the definite integral from 0 to 10. Sorry, this one would be 8 of f. This would be f of x dx again. And now we interpret this as the net area. So all this positive area that adds up to 15.5, subtracting this area that adds up to 2, and we get 13.5. Next video we record, we will talk about, transferring back and forth between these different representations, the definite integral symbol, the graph, and representing them and thinking of them as the connection between the function and the area.